Okay, I think we're at about start time. So welcome back to the second conversation we're having about AI and its practical applications today. Once again, I'm joined by my colleague Conan. Conan, welcome back. Good to see you.
Good to see you again, Phill.
Great. So excited to have this conversation that we're going to really cover a little bit of history about machine learning and get into some of its practical uses today. We want to build on our first conversation we had back in December. We've taken a bit of a hiatus. We're back and recharged and ready to go. But we talked a little bit about machine learning in the first conversation, Conan. We obviously learned a little bit about you, about some of the applications of this technology. But today we really want to dive into machine learning 101. So class is in session. We're back. We're joined by Professor McMurtry, and we're going to do a bit of learning today. So Conan, I thought what we could talk about is maybe first just try and set the scene in a bit of background about machine learning itself. You know, what preceded it, how do we get here from a intellectual, academic, applicative level, and then maybe get into a bit more about what makes machine learning possible, get into a few examples of different machine learning areas, and maybe at the end we can just talk a little bit about some predictions for the future.
Absolutely, yeah. So, yeah, we can start on a few things in there. So I guess, why do we need machine learning? We need machine learning, and we've needed it for a long time, whether we called it that or not, because since we've carried out scientific experiments, we need to find patterns in data.
Right.
We need to make generalizations out of data sets that we don't necessarily understand.
The basis of all experimentation.
Exactly.
Right, yeah.
Exactly. So, I mean, that's why we need machine learning, and today we need it more than ever.
Yeah.
But a lot of the basic building blocks of modern machine learning that have proliferated in sort of popular technology recently, they actually go back. They have a long, long history dating back at least 200 years.
No way.
Yeah. So, for instance, linear regressors and logistic regressors are things that were discovered in the early 19th century.
Mm-hmm.
And those are widely used by the biggest technology companies in the world today. So there's nothing new there. Then also, even when you start looking at the first experiments with neural networks, the very early neural networks, such as the perceptron model, which was invented in the 1950s, they were actually just iterations on the ideas behind linear regressors and so on.
But more powerful and able to kind of take on bigger data sets, or what will be the big difference there?
Yeah, so the sort of the shift in the discovery, the more recent discovery was that a particular type of perceptron that had layers stacked upon each other sequentially could theoretically, according to something called the universal approximation theorem, learn anything, theoretically. Could learn any function, no matter how complex it was, learn to approximate any data set, to put it a different way. So those discoveries started appearing in the 1950s, and in the 60s, you know, people were implementing perceptrons, but you'll find that due to a lack of computing power and resources that just weren't available back then, you needed a room to fit what today would be the tiniest neural network that could run on the smallest Nokia mobile phone.
So we made a lot of progress academically, but then obviously there was a bit of a lag in terms of what we could apply, computing power being one of them.
Exactly,
yeah.
Exactly. This is probably what led to what's called the AI winter that kind of starts in the late 1960s, when there was a bit of disillusionment in you know, a lack of results in machine learning.
Yeah.
And in artificial intelligence, the more successes appeared out of knowledge-based systems. So, for instance, in the mid-60s, there was an experiment by an American psychologist who designed a computer system that would speak, that would converse via text with users, and it was pretty convincing. All of the modeling behind it was just based on sort of grammar modeling and knowledge-based modeling.
Okay. So in that case, the programmer, you know, the psychologist in this case, he would and their team would actually encode the knowledge, so to speak, right? They'd actually impart the rules, and they'd set that framework down so that you'd have a, you know, real life human on the other side interacting, right? So
exactly.
they'd have to craft and imagine every iteration of the conversation.
Exactly, exactly. So it was all, they would have to pre-plan for most eventualities and try to find generalizations there. The experiment was called ELIZA. If the audience wants to look into it, it's pretty interesting. It was basically a software that would throw questions back at people. So if you said you'd had a bad day, then the software would say, oh, so why was your day bad? And you would say, oh, because I felt very tired. And they would say, oh, well, why were you tired? And so on and so forth. And you're going like that.
Must have been a pretty big breakthrough in the 1960s. Today we're obviously used to it with chatbots, but
definitely.
It must have been pretty, I guess, pretty wild for a machine to be talking back to you.
You've never experienced that.
Yeah, interesting. But obviously, it seems to me that what we know now, when we think about knowledge-based systems, it seems like it's pretty clunky to scale, right? You've got to try and encode all that knowledge into eventualities, and makes it just difficult, right? A lot of time to get probably a pretty small return on investment.
Yeah, definitely. So that's the promise of machine learning, that you don't, because it's difficult to scale something where you have to model for every eventuality, where you have to find the generalizations through that kind of human like semantic modeling. If you can learn from data, then you can potentially learn anything. You don't need to learn specific attributes of English or French or Chinese. You can just feed the data from any particular language and learn that.
Right, and then that's the real, I guess, the distinguishing facet of machine learning, right? Is this idea that you don't need to program it; it will learn by itself effectively. Is that how you would, or maybe you can define it a bit better than I can?
No, you've done a perfect job. That is exactly the definition of machine learning.
Right.
Definition of machine learning is a computer software that learns the desired behavior without having to be explicitly programmed.
And that's obviously the very big, the gulf between these knowledge-based systems and machine learning. So, okay, so interesting. So we've had this sort of this AI winter. I'm imagining AI researchers being kind of shunned on campus and not really given very much sort of serious consideration. But obviously that's changed now, and the tables have turned. But we've had this time where AI kind of goes out of fashion. Machine learning goes out of fashion in the academic track, but then obviously something changed, right? Because we're now using this stuff, and it's probably about 20 years ago now that we really start seeing application, starting small, obviously, but then going out and even today being kind of made commercial. So, what do you think changed? What made that first step in application possible?
Well, a couple of things changed there. The one that we already mentioned is that what we've seen is a proliferation of computing resources. People on their laptops can now solve machine learning models, can optimize machine learning models that it would take 2 rooms full of servers in the 1960s, and 100 years ago, a room full of number crunchers, solving the equations.
Complex problem.
Exactly.
Yeah.
So that's one reason. The other interesting one is that up until the 1980s, a lot of physics researchers were sort of kept well fed because of the Cold War and all of the work in, for instance, the space race with Russia and the U.S. and
so Star Wars, the Reagan program, funneling a lot of money into that. Yeah.
Exactly, and also like nuclear engineering and things like that. As soon as the Cold War started thawing, a lot of those physicists found themselves out of a job
on the breadline.
And interestingly, a lot of them started moving into machine learning. A lot of them seem to find a natural home there. And even a lot of concepts that used to describe things in physical theories like entropy are actually like widely used in machine learning, and also things like information theory with slightly different definitions.
Interesting. So there's actually there's like a geopolitical foundation for a lot of the knowledge transfer, the expertise that got injected into the space, and it sounds like it accelerated it.
Definitely, yeah.
Interesting. I wonder. It's always funny to think about what geopolitical forces have advanced science in different ways, hopefully for the better in most cases. But okay, so that's another one. So we've got computing power, we've got this kind of glut of talent going into machine learning and AI disciplines. There's probably a few other things, right, that we've missed. What else has kind of made machine learning possible?
So also the communications technology, the improvement in the speed at which we can communicate and the number of people we can communicate with allows for information sharing, knowledge sharing.
Yeah.
You have online open source software projects, for instance, is one example.
Yeah.
So I think that's also contributed not only to machine learning here, this is quite a general thing,
Sure.
but it's obviously accelerating something, and any information-based technology where most of the assets can be shared with information. All of those technologies are going to accelerate with the kind of communications we're capable of today.
Yeah, got it. No, that makes sense, and I think as you said, it's not just AI, but it's been so many academic disciplines that have benefited from open ideas and more sharing. I guess that's just the modernizing of academia writ large. So interesting as well. And then I guess the only final area is probably just data and storage that kind of makes that go through.
Definitely, yeah. The quantity of data that by necessity we need to process today.
Mm-hmm.
It almost demands that there be machine learning to do it. There's just nothing else to do with it. The data we're generating now, it's I don't know how often it's doubling every month or whatever.
Yeah.
So by necessity, we need to make sense of that information to be able to function, and as our economies develop and grow, so that's there too. Yeah.
Yeah, got it. And I guess it's not only the collection of data, but the storage of data, right? I read this pretty cool stat. I think it was on with one of the MIT review articles, and they were talking about I think how a gigabyte of data 30 years ago cost literally millions of dollars, and now it's 15 cents a gigabyte or something insane. So it's sort of it's halved every 14 months or something astronomical like that. So
yeah.
That's obviously a big contributor as well. So we want to talk about a few different areas of machine learning. But before we do, can you maybe break down just some of the main areas? So we've got things like supervised. We can talk about that a little bit.
Definitely, yeah. So let's speak about three broad areas in machine learning that that are probably the main classes. They would be, like you mentioned, supervised learning, unsupervised learning, and reinforcement learning.
Okay.
Right. So to explain all three, we can think of an analogy of some being that's in the forest and is trying to learn. So if this entity knows already what trees are, it's been taught at some point that that a tree is a certain way, a rock is a certain way, and a fruit is a certain way, then a supervised learner is given that information in advance when it trains. And then its goal is to predict on new trees and new rocks later that it's never seen before. So it learns how to recognize those different groups from the data, right? The data already contains explicit information about what those things are, and then it goes and makes predictions on new ones. On the other hand, an unsupervised learner doesn't actually know anything. It just has all of this new data with no labels. So it's in the forest, there are these things around, and it needs to somehow start to figure out that there are things that look somewhat similar, have similar characteristics that are, trees, let's say. And there are other things that have that also have some similar attributes that don't look like that, and those are rocks and fruits and water and so on. So an unsupervised learner is doing everything from scratch that way.
Right.
And that's when you hear about things like clustering, data clustering, trying to group things in different ways. That's what's happening there. So the third class in machine learning, the third area, reinforcement learning. That's if you imagine a squirrel in that forest, and the squirrel wants to eat, right? And to do that, it needs to act. It needs to search for food. It needs to develop a strategy. It needs to possibly store the food, right? Because it has long-term goals. It doesn't just want to eat everything today. It needs to be able to eat next week and the week after and so on. So it acts, right? And that influences its environment. It can, its new experience of the environment is that it's moved over here, or it's crossed the river, or it's climbed the tree. And its reward is whether it's found food.
Right.
Right. So a reinforcement learner is continuously trying to increase its rewards by acting inside some environment.
Interesting. Okay. And we're going to talk a bit more about reinforcement learning and sort of what's made it possible, and get into a few examples. The other area we wanted to talk about, and I guess there's probably examples of both supervised and unsupervised methodologies, but is deep learning, right? So deep learning we also call neural networks, depending on who you speak to. Why we just call it neural networks going forward. But talk to us about that, because I think that's something that people hear a lot of this, dare I say, jargon, especially around deep learning and so on. And I think this is also where some of the, I guess, ethical considerations come in when we talk about hidden layers. We'll talk about that in a second. But maybe first of all, you can just define what characteristics neural networks have, and why that makes them interesting, why that makes them special.
Definitely, yeah. So neural networks are sort of a simplification, a simplified model of how we believe neurons might be behaving in biological brains. And what a neuron does is it takes inputs from multiple sources, and then it sort of reweighs them, right, depending on their importance, and outputs something new. So it's sort of like an agglomeration of a number of inputs that have been reweighed depending on their importance, and then something new is created on the other side. A neural network is basically some model that has stacks of those neurons, both in parallel and in sequence, right? Got it. The simplest kind of neural network, a multi-layer perceptron with 2 layers, would have some stack of neurons, right? Which outputs, a set of, each neuron has an output, and then another stack of neurons that takes all of those new outputs as inputs and creates your final result.
Makes the prediction on the back of it. Okay, exactly. Got it. And you mentioned this idea that you can have different inputs producing new outputs. So what does that mean, or what's the implication there for the kinds of data you can predict on?
So the reason, in my view, the reason neural networks have become so popular today is not necessarily always because of their accuracy or them giving a significant improvement over other model types, but because of their flexibility.
Right.
Because basically the nature of neural networks makes them able to process almost an arbitrary range of data types. You can design neural networks, usually convolutional neural networks, to process image data. So to take images as inputs, or even to produce them as outputs.
Okay.
You can also process sequential data, data that has a time dependency, such as language information, sound information, music, people's voices, any other kind of sound. Even things like video. Right. Anything with a time dependence, you can use a recurrent neural network to either input that kind of information and get some different type of information on the other side, like a label. This is a cat. This isn't a cat. Or this is Phil's voice, or this isn't Phil's voice. Right. Or an input of Phil's voice and an output of Phil's face. Right. Right. Okay. So any kind of input, any kind of output, you can probably find a neural network that can make that transformation and learn it. And that's that kind of flexibility, I think, is what's creating the popularity behind it.
It's pretty powerful. Yeah. So before, you'd have to probably explicitly design the framework so that you could have those different, the input being different to the output, but obviously you don't have to necessarily hold that concern if you've got a different output that you want to predict on. Okay, that's really interesting. So it's that kind of the flexibility, but not necessarily the accuracy. You said not necessarily the precision, but it does give the user that level of flexibility that makes it powerful.
Definitely.
Are there any? I'm thinking about a real world application. Are there any examples that kind of come to mind that you could say is an interesting use of neural networks in the world today?
Absolutely, yeah. We can think of even so from the point of view of customer service software.
Obviously close to home for us. A little shout out to ourselves. Yeah.
So you can imagine a recurrent neural network that would take sequences of language as the input and create sequences of language as the output. So you're transforming a sequence on one side and you're outputting a sequence on the other side. So for instance, someone poses a question, that's the input. The neural network outputs an answer. That's how you respond to the query.
Got it.
You can think of examples, again in customer service, that there's a lot of research happening today for artificial customer service agents that are actually produced with photoreal video. So an artificial person that is some neural network generating that video that's responding to your facial expressions, responding to your language, to your gestures, and trying to satisfy some problem that you have.
Interesting. Okay.
Yeah.
Okay. So it's obviously a long tail of use cases. It's interesting to see. That's kind of how you can start thinking about application of neural networks. And we want to talk about one more type of machine learning area, and that's we talked about it earlier, reinforcement learning, and it's something I guess that's just kind of coming into its own now. The last 2-3 years now, or 3-4 years. You mentioned it already with the example with the squirrel. So it seems like it's kind of this rewards-based kind of AI algorithm or machine learning algorithm. What other characteristics does it have, or how else would you want to define reinforcement learning? Yeah,
so some things I mentioned briefly, but are probably important to repeat. A reinforcement learning algorithm is one where you have an agent, usually to refer to them as agents. They have some way of reading their environment. So with a robot, for instance, that could be via sensors. They act, so they have a range of actions that they can perform. And after performing an action, they will read their environment again, notice the change, interpret the change in the environment as a reward, right? And then the algorithm will be modifying how the agent acts from its range of possible actions to increase its reward, or sometimes also to decrease its punishment.
Got it.
An example, there's a video on YouTube, anyone can go and watch this, is a robot with a reinforcement learning algorithm and some sensors. The researchers would smack this robot over continuously, just knock it over, it would get back up. Its reward was not to fall. That was how it was programmed.
Right.
Eventually, you'd notice the robot start stepping out of the way of the research attempts to knock it over. So that's sort of the basics there. The other important thing to mention is that reinforcement learning is very interested in long-term planning, right? It isn't difficult to come up with greedy algorithms that the squirrel sees the food there, and it just goes for it, right?
As opposed to a squirrel that would, in our use case, store the food away, hibernate, and then come back.
Exactly. That would do a little bit of long-term planning, right? Store some food away to make sure that it also has food in 2 weeks.
Got it.
So long-term planning it's mathematically a much harder set of algorithms to work with, and there's a lot of work that's been happening there recently and a lot of progress. People have seen the news about the DeepMind's AlphaGo software beating world champions. Now their software is beating people at more complex games like StarCraft and things like that.
Got it. Interesting. Okay. And with reinforcement learning, so we talked a little bit about the kind of the games use case, and I guess AlphaGo was, I want to say 2015 when that was 2016.
I think it might have been 2016.
Yeah. So a few years ago, that's I guess been the watershed for its application. And we were talking yesterday, and you mentioned actually one of the reasons that reinforcement learning has become popularized is because of Google and Google DeepMind, right?
Yeah. So that's a very interesting point. Yeah. So reinforcement learning was not really a household name. There's a before and after Google acquired DeepMind, and the co-founders at DeepMind were mainly reinforcement learning researchers, and their first famous demo that went along with their acquisition was of their reinforcement learning system, learning Atari games and becoming sort of prodigious at these simple Atari games, Pong and so on, very, very quickly. So then after Google bought DeepMind, obviously they must have seen something. They must have developed an interest in reinforcement learning. We've seen them produce a lot of the major research. Most current reinforcement learning systems that are successful also actually involve neural networks that are part of the system that makes those actions, that makes those decisions within some sort of baked inside some kind of reinforcement learning algorithm that's dealing with the rewards and so on. But yeah, there was definitely a before and after that M&A event.
Their watershed. Yeah, interesting how some of these, when there's investment in a specific community, and we saw this, I guess, on a bit of a larger scale with the post-Cold War scientists, but how that can really snowball and take on a bit of a life of its own. One thing I wanted to ask ask you about, Conan, was we had this this concept of hidden layers with neural networks, just to go back a second, where what's going on between the kind of inputs and outputs is a bit kind of it's hidden. It's unclear exactly how the model is getting to that outcome. As a layman, it sounds to me like that's less the case for reinforcement learning, because you can kind of see there's an input that either incentivizes or decentivizes the machine learning agent to take an action. Is that the right understanding, or is there some hidden elements within reinforcement learning too?
Yeah. So I guess with reinforcement learning, you might face the same problem if you have neural networks in there. This kind of black box problem.
Yeah.
Because even though you know that the model is trying to learn how to maximize its rewards, you might not know too much about why it's doing it, which parts of the environment it's responding to. I think even with the AlphaGo research, there were some very strange decisions that the system would make that probably a human would never recommend.
I read that. Yeah, and then there was some steps taken that experienced AlphaGo players or Go players, that said the AlphaGo was taking decisions that they never would even conceived of.
Yeah. So with neural networks in general, you face that problem of the black box. You don't know which parts of the input data are necessarily influencing what the machine is doing. If you're trying to predict credit scores, if you're using what's called a linear model, you can fairly easily tell that, if you do an analysis, you can see that the things that are predicting a higher credit score are maybe income or postcode or that kind of thing. Whereas with the neural network, it's much, much harder to sort of analyze that information.
Right. Okay, got it. And then just finally, I guess, final question on the reinforcement learning models. Just curious about some applications where you think this could be useful. Obviously, we talked about games, we talked about StarCraft and Go. Where else do you think this might have a home and make a difference?
So, I mean, any application where a software needs to adapt dynamically to some need, you're probably going to see a need for reinforcement learning there, particularly in robotics.
Yeah.
Where it's in your interest for your robot to maybe protect itself or to speed up the rate at which it can deliver packages, or a self-learning car would try and optimize its time to destination or the safety of the passengers, that kind of thing.
Fuel efficiency, potentially, how fast it goes and the time it takes to brake the vehicle.
Exactly. Okay. We're also going to see some applications that might be a little bit more controversial. You will see reinforcement learning systems trying to optimize a person's willingness to spend money on certain products, to spend money at restaurants maybe. And how it's doing that, we might not know exactly why it's making those decisions. So there's going to be debate around that, and there already is. But I think anywhere where you see a need for a software to work towards a goal, that is usually in the interest of the people using the system, you'll see reinforcement learning.
Yeah, got it. So that sense of the dynamic environment, right, where you've got recently like manufacturing, where the machine is incentivized to perform certain tasks that lead to higher maintenance costs, or I can see an IoT use case potentially where your fridge is running on empty and there's certain behaviors that you could take to kind of calibrate.
Exactly.
Okay, that's interesting. So that's what we've kind of got in the very much in the world today. I guess the final topic I was interested in kind of picking your brains on, Conan, is just, what do you think is next? Are there interesting trends that you sort of see before us, or interesting machine learning areas that you think will pick up steam in the next couple of years?
Yeah, that's a great question. Well, we are going to see things appearing in the next years that we haven't heard of today, but that I'm certain of. There's still a lot of problems to be solved. And more recently, in the last couple of years, there's been a developing interest in multi-agent systems. So we were talking about agents in the reinforcement learning context, an agent that is working in an environment. So clusters of these agents all working towards solving a common goal. So an example might be, let's build on the example of a robotic restaurant service, right? A waiter might be trying to optimize the customer's sentiment and the customer's willingness to spend. A cluster of agents might be together trying to optimize the total takings at the restaurant at the end of the day.
Yeah.
or the total profits as well.
Mm-hmm.
So clusters of agents that are working towards common goals, multi-agent systems, that's there's a lot of DeepMind as well are kind of leading the way with that. There's a lot of work happening there. Another interesting development, and again, it's a similar concept. Things are moving towards these groups of machine learners that are in some way working together to solve problems.
Yeah.
There's a thing called a generative adversarial network that is from a different point, it's from a slightly different point of view because they're actually competing. In a generative network, adversarial network, you have one part of the system is creating data, right? And it's trying to fool the other part of the system. The data it's creating is real, right? So you have a source of true data, and you have this trickster that's creating false data, and is trying to trick this other machine learner to believe it's false data. While the other one, on the other hand, is trying to improve and get better and better at finding out the trickster.
Okay.
And as you progress, they both get better and better. Right? So once you've trained the system, the trickster has become very good at creating this fake data. Right? And this system has had incredible results in things like generating photoreal images. So you can input the characteristics, a young, Asian woman with glasses, and it will generate a photoreal impression of a person with those characteristics. Wow. Very, very interesting results there with adversarial networks. So those two movements just now, they kind of seem to fall under the hood of this idea, this concept of machine learning systems that are separate and work together to solve problems.
Yeah, producing some kind of result, some kind of outcome. But I guess both of them are still sort of relatively speaking in their infancy when it comes to application. Although a few things have surely come to pass. But very interesting. Great. Well, Conan, thank you so much for the conversation today. I've really enjoyed it. I hope you have as well. Thank you for taking the time to listen to this conversation. If you do have questions, let us know. You can reach us at hello@digitalgenius.com. And Conan and I will be back next month. And we're going to talk about something that is pretty close to our hearts here at Digital Genius, which is conversational AI and some of the opportunities, some of the challenges it poses. And we're looking forward to continuing the conversation with you then. Thank you.